Now we want to take a look at surface area. So this is going to be taking what we were doing similarly to our volumes. We're going to take a curve, like say this function y equals f of x that we have graphed here, and we're going to rotate it around the x-axis in this case, and we're going to get our solid here. And again, we could kind of put a little circle in here to help us see how that's in 3 dimensions a little bit more. Kind of looks like a little bit like an hourglass turned on its side. And so now instead of trying to find sort of that inside volume, what we want is the surface area. So it's the difference of, versus volume, we're trying to say, fill this with water, uh, versus now we want to say, okay, what if I wanted to paint the outside of it? How much paint would I need? So just like anything again that we do in 252, we're going to take this region that we want to find the surface area of, and we're going to chop it up into little pieces, and we're going to find the surface area of each of those pieces, and we're going to then add them up. So we're going to kind of take a little something like we did with the arc length, where we're going to, here's x sub 0, x sub 1. We're going to find the line that connects those y values, and we're going to take this region that kind of looks like a trapezoid, and this is what we're going to rotate around the x-axis, and we'll get this kind of, it'll look like a cone that's had the top chopped off of it, right? Because it's going to have slanted sides. Um, and sorry if you heard that ding. I always get text messages while I make videos. Gotta tell people. I'm gonna get one more, I can tell you right now. So we're gonna make these sort of cones with that lid sort of chopped off. Now, just like with everything, we're gonna make these strips smaller and smaller and smaller. And as we do that, the side, it is going to be slanted, but it's basically going to turn into us having a cylinder with kind of a slightly sort of slanted out side. So if we think about what the surface area of a cylinder that has, no top or no bottom, so it's a pipe, no bottom here. It's just going to be, the surface area of like this outside part here. And that's just going to be 2 pi r times the height. So what that is that we've got to get the circumference here of all the way around, because remember, this is like we have that oatmeal container that we've cut open, and if we open it up, it will look like our rectangle. And this will be almost a rectangle, it'll be close enough. So circumference gives us our length, and then the height is going to be that sort of slanty edge there. Well, if we kind of think about this now, this 2 pi r times the height, that radius, we can view that. We could take, some point in our interval and get our radius. So we could do it there, or we could do it here, or, we could take something that, if we've got one, none of these are very good approximations, but we can take it at, sort of the best place that we think this approximation to our radius. But that's going to be the height of our function, basically. It's going to be f of x. And we could maybe grab a point where it is one of our heights um, of our function there. So we're going to have f of x sub I, and we'll put a little star in there because it could be an endpoint, but it doesn't have to be. And then we're going to have the length of the slanted side there. And we can get that from our arc length. So arc length, we know we just did that in the previous video. Let me not be the red pen anymore. So we'll have 2 pi f of x sub I star. And then the length of our slanted side will be the square root of 1 minus f of x sub I, sorry, again, it keeps dinging there, times our delta x. So that is our arc length, because that is going to give us that side that we need. So it really is just the arc length of our curve times 2 pi times our radius, like how high up that function goes. And of course, for our total surface area, because this would just be for one sort of slice that we have, our total surface area is going to be the sum from I equals 1 to n of this 2 pi f of x sub I star, and then 1 plus f of x. Oh, derivative. I forgot the derivative. Oh my goodness. That would have been bad because we do need that for arc length. We'll put parentheses around it there and we'll get delta x. Sorry, my handwriting is not the greatest today. But then we, of course, will take the limit here as we go to infinity because we want to make more and more slices. And as we do that, that will limit out to give us the integral from, not 0, it's going to be from a to b of 2 pi f of x, and then our arc length in there. So this is really pretty much the same. Oops, we don't need those subscripts anymore. This is pretty much exactly the same as our arc length, but now we've just got this sort of extra little part right here that gives it that dimension to it. And I again grabbed our theorems out of our book, and it doesn't really matter if we define our function in terms of x or in terms of y. The surface area is the same either way. Now, most of these are going to be pretty difficult for us to do by hand. There are going to be some that we can. This one we can do by hand, and I'm going to show us here. So again, the idea is that we're going to rotate this function around the x-axis and create that three-dimensional shape. I didn't get a very good curve on that. I'm recording this in the afternoon, so my drawing is not as good as it was earlier in the day. And again, the idea is that we're going to take, this slice of this like that, and we're going to get our surface area. So just like with the length of our curve, I'm going to start by figuring out, what's going to be under that square root. We're going to start there. And I'm going to take it piece by piece. I'm going to find the derivative of this function that we want to find the integral of, or the surface area of. Sorry about that. So we get 1/2 times 1 plus x 4x to the negative 1/2 times 4. Simplifying this just a little bit, that's going to give us 2 with the 4 and the 1/2 canceling, and then we're going to have 1 over the square root of 1 plus 4x. Then we want to square this. All right, so we'll take this function and we'll square it. This is going to be nice because this is going to actually get rid of that square root. Hooray. And it makes the top a 4. And yep, we're squaring a square root, so that goes away. And then when we put this underneath a square root and add 1 to it, we're going to get 1 plus 4 over 1 plus 1 plus 4 over 1 plus 4x. There we go. And so what I want to do is actually add these two terms together. And that's not very difficult because we can get a common denominator on 1. That's sort of the easiest thing to get a common denominator with. We just need to do that 1 plus 4x on the top and 1 plus 4x on the bottom. And then we can add our numerators and we get 5 plus 4x over 1 plus 4x. All right, so this right here, again, this is what's going to sit right here in our integral. So we figured out sort of that kind of complicated part of it, and so we just have to plug that into our integral. So here we're going to have the integral from 1 to 5 of 2 pi times f of x, so our function, and then times what we've got circled there in red, which I'm going to split up as the square root of the top part and the square root of the bottom part of that fraction, which again, we can do that. That's allowed with our square root rules. And hopefully you see exactly why we would want to do this, because those cancel. The one that's on the top and the one that's on the bottom goes away. And this leaves us with an integral that we know how to take. We can pull that 2 pi out in front, and then we've got the integral from 1 to 5 of 5 plus 4x. We do have to do substitution to take this integral. So we need to say that u is going to be 5 plus 4x, and then we're going to get 1/4 du is equal to dx. We're also going to probably want to change our limits of integration. So I think I'll plug in a 1, and what do I get? I get 9, and we'll plug in 5, and I will keep the colors the same so that you can see when we do this, how things change. Okay, sorry, I was like looking at something. Oh, it's like trying to figure out why this wasn't going to work. And then I realized, oh, that was supposed to be a 4. There we go. That's 25. All right, so after we do all our substitution, we get 2 pi, and we'll have the square root of u there in du. Oh, we need to get our 1/4 in there, our 1/4 du. That's replacing our dx. And our new limits of integration, 9 to 25. So our integral, we're going to get what? 2 pi times 1/4 times, we're also going to get a 2/3, and we're going to have u to the 3/2 from 9 to 25. Because we changed our limits of integration, we don't have to substitute back. And if you take a look at our coefficients, we've got a 2 right there, a 2 right there, and a 4 on the bottom. So all of that cancels, and we're left with pi over 3 u to the 3 over 2 from 9 to 25. Again, I'm trying to kind of, keep our steps a little bit slower so we don't go too far ahead, and then plugging in each of the numbers, and we end up with 125 times r pi over 3, and then 27 times r pi over 3, and we've got common denominators, so we just need to subtract those numerators, and we get 98 pi over 3.